Okay, so we'll still hand out problem set 5 on Thursday the 6th. That'll be a review problem set for the midterm. We'll grade it as well. I'll talk about that more on Thursday. But in the handouts, there will be 5 days during which you'll have 2 problem sets in your possession, violating the law of conservation of problem sets momentarily. I apologize. Okay, so that's problem set 4. One other sort of policy that I'd like to change slightly. You'll recall that your grade in this course depends half on the problem sets and half on exams, and we'll have a total of 10 problem sets. I'd like to modify the policy about how we evaluate the problem set grades slightly by dropping from your score your worst problem set. So that'll accomplish 2 things. A few people came into the class a little bit late and so weren't able to turn in problem set 1, for example. That hopefully will be your lowest problem set score. So we'll just omit that. The rest of you, if you have a bad day or need to put on a problem set for whatever reason, we'll drop that score. Yeah. Yeah, that'll be due on thanks for reminding me. So that'll be due on Tuesday as well. I should have so last Friday we got out the documentation for that problem set. It's in a file called codebook.doc, I believe, in the resources section on BSpace. There's not very much in the documentation, but that's what that is. Okay, other questions about administrative matters? Yes. No, so the midterm. I'm not changing the date of the midterm at all. That'll remain on the 13th, so a week from Thursday. Yeah. You'll be happy when it's over. Okay, other questions? Okay. All right, let's go ahead and get started. We have a lot I want to cover today. So we talked last time about the consumer's dual problem. So you'll recall that the dual problem for the consumer is the problem of minimizing expenditures subject to attaining some specified level of utility, which we've been calling U-star. So that's the dual problem. So you saw this slide or something like it last time. There's an expenditure function. It's in fact defined to be the function that solves the problem I just described. So this function e of what have I done? There we go. So this function e of pu tells us exactly the answer to what's the minimum amount of money I need to spend in order to achieve a level of utility U star, given that I face price is p. So that's what that problem. That's the solution to the problem, which, as I said a moment ago, is minimizing expenditures subject to satisfying some minimum level of utility. Okay, we solved that problem last time, and the solution to the problem involved figuring out how much of the different goods you should demand, given that you face price is p and need to achieve a level of utility U star. The answer to the question, how much of different goods should I buy to attain that level of utility, is given by the Hicksian demands, which we're using little letter h's to denote. Okay, so one way to compute the expenditure demand is just to plug the Hicksian demands in here. I did that last time for you. So if you compute the Hicksian demands by solving this problem, you can just plug them in, compute the expenditure function. And for a particular example, the example utility function we worked with last time, it turns out that the expenditure function takes this form. So when we have utility, I should probably write this down. When we have a direct utility function that takes the form u of x1, x2 equal to alpha 1 log x1 plus alpha 2 log x2 with alpha 1 plus alpha 2 equal to 1. So that's the direct utility function. We wind up, well, maybe we should just write this down, actually. What do we get for an indirect utility function? Does anyone recall? This might be kind of nice to have. Actually, what do we get for Marshallian demands? So what's the demand for x1, for example, of p, y? It'll be equal to alpha 1 times y minus p1 phi1. If we have, I'm sorry, hold on, I meant to add this in here, sorry. Minus phi1 plus log x2 minus phi2. There we go. So we'll need to subtract this phi1 here, all divided by p1. Okay, so that's the solution for the Marshallian demands. The indirect utility function in this case takes the form v of py. This will be equal to some constant a. We get this funny constant that will depend on the alphas. We don't really care what its value is so much. It'll be plus the log of y minus p1 phi1 minus p2 phi2. The idea, remember, is these phis are like subsistence levels. So if x1 is food, then you can interpret phi1 as being the minimum amount of food you need to survive. So the income you have, sort of your disposable income, if you like, is the income you start off with minus the food you have to absolutely purchase in order to remain alive. Of both, and you have to pay the subsistence levels for both food and clothing or whatever. Okay, so this is sort of like the log of your disposable income. We're not done though. And then you subtract alpha 1 log of p1, alpha 2 log of p2. Okay, so that's the form the indirect utility function takes. Is it all clear? This is all totally review. Might be handy to note down though, if you haven't read this stuff already. Okay, and then so here for the same utility function, I've written down the expenditure function. So the expenditure function for this system of demands is, instead of depending on prices and income, it depends on prices and some level of utility U star. It's equal to some constant. It's some constant we don't care about. I'm going to call it a prime because it's not exactly the same as this constant. Although it's closely related, I guess. Anyway, this thing times e to the U star times p1 to the alpha, p2 to the alpha 2. Sorry, p1 to the alpha 1, p2 to the alpha 2. And then we have to pay, the expenditures include the expenditures we need to make on these subsistence goods at the sort of a bare minimum. So we'll have to add p1, p1 plus p2, p2. So that's the expression you get for expenditures, which I just replicate what I have on the screen there. Okay. All right, so this is the expenditure function that comes from, that's associated with this direct utility function and with the consumer's dual problem of minimizing expenditures to achieve a level of utility U star. This is so far all review. Is it all clear? Any aspects of it unclear? And you'd like me to say something more before I go on? Okay, wonderful. All right, so I'm going to tell you another trick, which is useful. On this slide a moment ago, right here, I talked about using the Hicksian demand functions to compute the expenditure function. But just as you'll recall that we can ordinarily the way we compute the indirect utility function is to compute Marshallian demands, plug them into U, and get the indirect utility function. But we know that we can also start with an indirect utility function and work back to Marshallian demands. Does anyone remember the trick? What that trick is called? Yeah, thank you. It's called Roy's identity. There's an analogous trick that allows us to start with an expenditure function and get back Hicksian demands. And that trick is here on the slide. It's called Shepard's lemma. Anyone know what a lemma is, by the way? Yeah, so a lemma, it's often used, and this is the usage here. It's like a little result. It's usually a little result that's used to prove a larger result. It's a Greek term also. It means a horn. So it's the horn of an animal. It takes the word dilemma, by the way. A dilemma is something that puts you between the two horns of a problem of some sort. Anyway, so Anyway, so here's a trick that allows us to use the expenditure function to compute the Hicksian demands. And it's a very simple one. It just says that the Hicksian demand is equal to the partial derivative of the expenditure function with respect to the price. So let me go ahead and use so this is true for for any expenditure function, not just this one. But let me go ahead and use this one as an example and use this to compute the Hicksian demands that belong to this system. Is everyone with me on that exercise? So I just told you, I repeated what the Marshallian demand is. Let's go ahead and compute the Hicksian demands corresponding here by using Shepard's lemma. Okay, so what we'll get, let's do it for price 1. So I want to compute H1. And remember, what are the arguments for the Hicksian demand? What does the Hicksian demand depend on? It depends on prices and on this level of utility U star. So remember, it's the answer to the question, how much of good 1 should I buy in order, given price is P, to achieve a level of utility U star? That's the question. This is the answer. Okay, so this thing is going to be equal to just dE dP1 by Shepard's lemma. So let's go ahead and just compute this partial derivative. So what's this thing going to be equal to? Help me with the derivative here. P1. Okay, good. Yeah. So here, that's great. So P1 shows up in 2 places, here and here. So let's go ahead and work on this one. So from this thing, I heard someone say we're going to get the exponent. So this will be equal to alpha 1. And these things are just constants, so they're going to stick around. So we'll have A prime e to the U star. And then we'll have P1 raised to what power? Alpha 1 minus 1. And then we're holding this fixed. This is just still P2 to the alpha 2. And then what else do we have? Just this term here. So this Phi1 shows up. So we'll have a plus Phi1 showing up there. Now, this doesn't look too awful, but it has a really nice simplification that uses the fact that we have up here that alpha 1 plus alpha 2 is equal to 1. So if alpha 1 plus alpha 2 is equal to 1, then alpha 1 minus 1 must be equal to what? I'm sorry, I think I heard it, but it'll be equal to minus alpha 2. So this whole thing simplifies to be alpha 1 A prime E U star times P2 over P1 all raised to the alpha 2 plus V1. Okay, so that's the result then. So that's the Hicksian demand for good 1. I don't know. Since we're having so much fun doing algebra, what's going to be the Hicksian demand for a good 2? Let's answer that just by using a symmetry argument instead of taking the derivative. So we're going to do this. We're going to use symmetry, which means we're just going to read this thing. Where we see a 1, we're going to plug in a 2, and vice versa. Okay. So H2 of P U star then, people started saying it. So we'll have what? Alpha 2. And then A prime, this stuff doesn't depend on 1 or 2, so we'll just plug that in. And what about this piece? This is the tricky bit. We'll just, P2 becomes P1, P1 becomes P2, alpha 2 becomes alpha 1, and then we'll have plus V2. So again, just by all this by symmetry. And if you don't trust the symmetry argument, you can verify it by using Shepard's lemma. Okay. All right. Are there some puzzle books back there? Can you people read what I've written on the board here? Okay. Any questions so far? Okay. So we've got a bunch of connections between different mathematical objects here. We can start with the direct utility function. We know how to compute Marshallian demands. Given Marshallian demands, we can work out indirect utility functions. We can also go the other way. We can go from indirect utility functions to Marshallian demands. In the dual problem, and sort of everything below the line here is dual, we can start with an expenditure function and derive Hicksian demands, or we can start with the definition of the expenditure function we had here and solve this consumer's dual problem to get Hicksian demands. Okay, so we can go back and forth with these objects. Yes, Wes? Yeah, we'll see how it comes out. Oh yeah, I can do that. Sure. Yeah, and the arrows go different directions because you can use this, using Roy's identity to get to here. So that's one arrow. We can use maybe I'll write this, the primal problem, which is maximizing utility subject to a budget constraint. We can solve this thing given the utility function to get Marshallian demands. In the dual problem, we can solve the dual problem by starting with the expenditure function, which allows us to get, I guess we go from the direct utility function to the dual to the Hicksian demands, and from the Hicksian demands we can get the expenditure function. We can also get the Hicksian demands via Shepard's lemma, though. So it goes something like this. Okay. I'm not sure that clarifies things greatly, but I feel it's helpful. Yeah. Okay. Okay. Good. All right. Other questions about this? Okay. So this is really this is a pretty cool place we've gotten to technically. We have a bunch of objects here now that describe consumer behavior when prices change, when income changes, or when the level of utility you want changes. And that's going to be a powerful set of tools to use for a variety of kind of analysis we might do. So I want to spend some time today beginning to think about how to apply some of those tools to do some analysis. I'm not going to have much in the way of applications today, but I'm going to think about the problem of trying to account for how changes in price affect changes in demand. And in particular, where we're headed today is a discussion about two different channels, if you will, by which changes in price affect demand. And the two different channels go by the name of a substitution effect and an income effect. Okay. So the idea here is a simple one. If a person has a fixed income, Y, for example, then an increase in price will have two different effects on demand. And so let me try to draw. This may be the most complicated graph I'll try to draw for this course. So bear with me. I'll try to make it big and clear, and ask questions if something's not clear. So I want to go ahead and draw demand. Working in commodity space here. So I'm going to have goods x1 and x2, and I've got some initial indifference curve, and this indifference curve yields a level of utility U star. Okay, now let's imagine that there's some initial prices that this consumer faces, and so we know given that price, okay, so given that price, I'm going to call it, label this thing this P, since it's a vector of prices. So this is the initial prices. Given this price, that'll pin down how much of good 1 and good 2 the consumer will buy. We're basically, I want to think, because we're reading this off U star, and I want to think about this as pinning down the Hicksian demand. H1 of P U star and HT of P U star. All right, so far so good? So the way we haven't talked about this as much as we might have, I guess. The way Hicksian demands work is if we see a change in price, we stay on this indifference curve because we need to still reach this level of utility U star. So what happens if the price of good 1 doubles? How do we compute the new Hicksian demand? It'll change the slope. I mean, so if the price of x1 doubles and P2 stays the same, how will the slope change? How much steeper? Twice. If the price doubles, it'll be twice as steep. The slope of this line is P1 over P2, or minus that. So if we double P1, hold P2 fixed, the slope doubles. So let's see if I can do that. Something like this, I guess. Involves new prices. Let's call new prices P prime, and then this pins down a quantity H1 at P prime U star. So this difference is the difference in demand we get when price of good 1 doubles, but we stay at the same level of utility. And this difference that just comes from staying on the same difference curve is called the substitution effect. And you can see this difference is just equal to the Hicksian demand evaluated. Maybe I'll write it up here because I think my writing's getting low there. So we have prices change from P to P prime. The substitution effect is equal to H of P prime, I guess, U star minus H. I'll put a 1 there. H of P U star. So that's the substitution effect. So it's how much you would change your demand for good 1 if the price for good 1 doubled and you were to maintain the same level of utility as you started with. Is that clear, sort of conceptually, what we're measuring there? Okay, that's great, and a really useful sort of quantity. But it's less useful than it might be empirically. Yes, please. Yeah. Okay, yeah. So that's where I'm headed. So let me go ahead and take this original line and extend it to this origin. So the intercept here is what? Just y over P2. So when P1 changes, the intercept doesn't change. And your point exactly is that, boy, the intercept of this line certainly did. Okay, so there's something we're not taking into account, and that's the effect that this increase on prices has on what's sometimes called the real income of the consumer. So, in fact, what happens if prices double this good, it's not only the case that relative prices change, but also the real buying power, the budget set of the consumer changes. How does it change? Well, it still has this intercept up here. And so the budget set, so we get the change in relative prices from here to here. That's what allows us to stay on this indifference curve associated with U star. But the budget set actually has gotten smaller. So I should be a line that starts at this intercept and is parallel to this line. See how I can do parallel, something like that. It's not so bad. And so the problem, of course, is at this point that we shifted to isn't feasible. Our budget set doesn't include these points up here. Okay. All right. So there's a consequence for this, which is that if in fact prices doubled, we wouldn't be consuming this quantity of H1. We certainly wouldn't be consuming this quantity of H2. It's not even in the feasible set. So what would the consumer be doing instead? Have to go to a lower indifference curve. This one is not. There's no point on this indifference curve because it's in the feasible set anymore. And so think back to the primal problem. If this is your budget set now, the optimal point for you is going to be where you find a tangency between this budget set and an indifference curve. So that indifference curve is going to be I don't know how I can draw this. I'll try it. Let's say it's that. Something like this. So this really is, let me draw this a little bit carefully, this is x1 at P prime y, where y is now the new budget set. It takes into account that you don't really have the income to buy this bundle up here. Okay, so so there's a total change. So this quantity I've labeled H1 associated with U star here. This was feasible at the old prices, at prices P. And so this H1 at PU here is how much was demanded when prices were this. When prices change, in fact, demand is this quantity x1 down here. Okay, now we said that there's a substitution effect. That's just this change from H of P prime to H of P. There's also this other piece in here. This piece is called the income effect. So this is the change that comes about as a consequence of there being a change in relative prices, but also a reduction in the real income the consumer has, a reduction in the resources they have available. Okay, so the total change in demand here, so total demand change in response to a price increase is going to be equal to x1 of P prime y minus x1 P y, or the reverse of that, depending on how you measure the change. So this is the total change we'll actually observe when prices increase. It can be decomposed into 2 parts. It's equal to a substitution piece plus an income effect.